right, so the purpose of this section is to talk about how do you solve problems if they specifically tell you either that the population is not in Hardy-Weinberg equilibrium, or they tell you that they want you to test to see if the population is in Hardy-Weinberg equilibrium. So if a population is in Hardy-Weinberg equilibrium, then you can basically calculate Q from Q squared. If I take the square root of Q squared and I get Q, it should be the same answer I get if I calculate Q manually. Now, what do I mean by calculating Q manually? And this is where you have to understand the difference between an allele frequency and the frequency of individuals that are homozygous recessive. Now, this would be true for P squared as well, but I'm just looking at Q. So, for example, let's say that I tell you that this population is in Hardy-Weinberg equilibrium, and I can't just make up numbers here. I mean, there's certain things that it's only going to work if the numbers work. So this is a population that I know is in Hardy-Weinberg equilibrium. So there are a total of 200 individuals. And I also know that 50 of them are little b. So I know that 50 over 200 gives me Q squared, which ends up being 0.25. And if I take the square root of that, I get that Q is 0.5. Now, just to show you that this population is in Hardy-Weinberg equilibrium, we're going to calculate Q the long way. Now, the true Q of the population is how many out of all the letters, all the alleles in the population, how many of those are Q, are little b. So I'm going to use, I prefer this formula. Both formulas will technically work. So if I come down here, so in this scenario, I have 200 individuals. Isn't that true then? That I have 400 alleles. Why do I have 400 alleles? Because every individual has 2. So if I represent every individual's letters, I'm going to have, instead of 50, there's 50 individuals, but technically each of those individuals has 2 copies of big B. So these individuals are actually contributing 100 copies of big B, not 50. So out of 400 alleles, let's see how many of them are little b. So we're doing little b. You can do big B the same way. So I know that every individual that's homozygous recessive, over here, homozygous recessive, there's 50 of those, and each of them have 2 copies of little b, right? Everybody's little b. So if I'm counting letters, every one of these people has 2 letters. Plus, little b is how common, Q is how common little b is in the population. Plus, everybody who's heterozygous, they have 1 copy. Notice I'm not multiplying this because these 100 people have 100 little b's. Their other 100 letters are big B's. So that gives me 200 over 400 alleles are actually little b. And that's going to give me Q, and that's actually going to be 0.5. So notice how Q is the same, no matter which way I calculate it. So the true Q and P of a population are actually calculated by adding up all the copies of the dominant allele and the recessive allele over the total number of alleles in the population. That's how you would actually calculate it by hand, and those are the accurate numbers. The others, the Q's taking the square root of Q squared or P squared, that's a shortcut. And that shortcut only works properly if the population is in Hardy-Weinberg equilibrium. So let's go back to this problem. So if this population was in Hardy-Weinberg equilibrium, then P squared is going to be, so P squared is going to be 30 over 85. Why 85? So there are a total of 85 individuals here. 85 people, if this was people. Okay? So P squared is going to be 30 over 85, which would be 0.35. 2PQ, heterozygous, there's 50 heterozygous individuals over 85, and so that is going to give me 0.59. And Q squared, which is my homozygous recessive, there's 5 of those over 85, and that's going to give us 0.06. Okay. Now, if I was to calculate P and Q from that, I'm going to get an actual, I'm basically going to get the wrong P and Q. It's not going to match what I get when I do it this way. So let me show you. So if I do, although once we do that, we can't just say, oh, it's not an equilibrium. You'd actually have to do a chi-square test to say, was it close enough to be an equilibrium? So let's calculate P and Q by hand instead of using the P squared 2PQ method, right? So if there's 85 alleles, we're going to multiply that by 2. That means there's going to be 85 individuals. Times 2, there's 170 alleles. All right? So P, out of those 170 alleles, I see that everybody that's big B, there's 30 of those people, and each of them have 2 copies of big B, right? Plus the 50 that are big B, little b, they have 1 copy, and so P comes out to be 0.647. And now Q, I'm going to do it again using the long formula, since they're telling me in this question that they don't know that this is an Hardy-Weinberg equilibrium, and we're sort of testing that. So for every little b, there's 5 little b's. Multiply that times 2, because each of them is carrying 2 copies of that letter, plus the 50 heterozygous all have 1 copy. And I'm going to get a Q that's equal to 0.353. So this is P and Q. Now, notice, I can already tell this is probably not going to be an equilibrium, because if I calculated the shortcut way, sorry. So let's take our P squared that we got up here. So here, we got 0.35 was P squared. If I take the square root of 0.35, I get that P would be equal to 0.59, which does not match this P, 0.59 versus 0.646. So it's almost 10% higher. And same thing with Q. For Q, I got Q squared was 0.06, so the square root of 0.06 gives me 0.77 for Q. And that's way off from our calculated Q. So which one is right? This is right. It only matches the shortcut if the population's in Hardy-Weinberg equilibrium. So I can already see that this is probably not. But on an AP exam, they might actually make you go so far as to do a chi-square test to see. And I've actually seen this. So if this was an equilibrium, using the P and the Q that we know that are correct and accurate, how many individuals would we expect to be big B, little b, and little b, little b? Okay, so remember from our previous slide, P, when we calculated it by hand, which is the accurate calculation of P, is 0.647. And Q is 0.353. So these are the correct P and Q. So if we actually do P squared, so if I do 0.647 squared, I get 0.42. And if I multiply that times my 85 individuals in the population, I get an expected 36 should be big B out of my 85. For 2PQ, big B, little b, I'm going to do 2 times P times Q. That's going to give me 0.46. And then if I multiply that times the number in my population, I'm going to get an expected of 39 big B, little b. And then Q squared, taking the Q that I know to be accurate, is going to be 0.12. And I'm going to multiply that times the 85 in my population, and I'm going to actually expect 10 to be little b, little b. So these are my expected numbers. So it's going to be 36, 39, and 10. That's how many I expect to be big B, little b, little b, little b. Now, I don't have the formula. I know you don't have the formula sheet in front of you, but the critical value, the cutoff number for this is going to be 5.99. So to do chi-squared, we would do observed minus expected squared over expected, and that would give us chi-squared. So if you actually work this out, you're going to get 1.0, 3.1, 2.5, and that gives you a chi-square of 6.6. Since our cutoff is 5.99, this would fail a chi-square test. So our final conclusion would be that this is not in Hardy-Weinberg equilibrium. Again, there were a lot of clues, because if we go back, you can actually see here, remember, this will never go wrong. If you calculate P and Q by hand, this is accurate, for sure. The shortcut is not accurate if it's not in Hardy-Weinberg equilibrium. The shortcut should give you the same answer if it's in equilibrium. You could check other problems that we've done, and you should see that, that you are going to get the same answer. But in this case, you don't. So that right there, that's already a clue. You could use that as an explanation, that when you calculate P and Q by hand, the accurate numbers of alleles in the population do not match the expected number when you do the when you use the shortcut. But you can do a chi-square test that I've actually seen on a AP exam. There were a couple of questions, multiple choice, and I think they were both multiple choice, where they specifically asked you what your chi-square was. So you had to know how to calculate this by hand using those formulas for P and Q. These are not on the formula sheet, by the way. These P and Q by hand formulas, the only things on the formula sheet are that P plus Q equals 1, and that P squared plus 2PQ plus Q squared is equal to 1, and that P is the dominant allele, and that Q is the recessive allele. That's what's provided for you on the formula sheet. So hopefully working this problem kind of helps you to see how you could be asked about a population that is not actually in equilibrium, or asked to test if a population is or isn't. If they tell you the population is in equilibrium, then it's cake. Because if it's in equilibrium, all the shortcuts work. So all you have to know really is how many of them are recessive, and you've got Q squared, and then you can simply take the square root of that to get Q, and you can get everything else from there. But that's not going to work if they tell you it's not in equilibrium.